Today, we're going to look past the surface of the code we write every day. We're going to uncover this hidden structure, this really beautiful map that compilers use to understand and, to optimize our work.
So let's just dive right in. Have you ever really stopped to wonder what your code looks like to a computer? I mean, what does the compiler actually see? It sounds like a simple question, right? But the answer is, well, it's way more interesting than you might think.
From our point of view, it often just feels like a list, a simple, linear script, kind of like a recipe, where the computer just follows each step, one after another, from top to bottom. But the reality is so much more dynamic than that. Hidden inside that straight line of text is this incredible map of possibilities. It's like a whole network of roads and intersections and different destinations that describes every single path your program could ever possibly take. Okay, so why should we care about this hidden map? What's the big deal? Well, because understanding it is the absolute key to figuring out how we make software faster, more reliable, and a whole lot more secure. It's all about learning to see our own code through the eyes of a compiler. The source material for this really puts it perfectly. It says that by analyzing this map, a compiler can do these things called data flow optimizations. And this process generates machine code that's so good, it actually resembles code written by a skilled programmer. I mean, think about that. It's like having an expert go through and hand-tune every single line for you to get the absolute best performance. And the applications here are just huge. Seriously, this is not just about speed. This kind of structural understanding lets us find really subtle bugs before the program even runs. It helps us spot security holes before they can be exploited, and it even helps engineers design the very next generation of computer processors. It's that fundamental. All right, so how do we actually start drawing this map? Where do we begin? Well, the very first step is to find what you could call the straightaways on our map, those uninterrupted stretches of road. And in compiler speak, these are called basic blocks. And the formal definition is honestly beautifully simple. A basic block is just a chunk of code with one way in and one way out. That's it. Once you enter a block, you are absolutely guaranteed to run every single instruction inside it in order without any detours. No jumping in or out from the middle. It's a complete straight shot. Okay, let's make this real. We're going to take a simple piece of what's called intermediate code. Think of it as a low-level version of our program that the compiler uses, and we're going to find its basic blocks together, step by step. So the whole key to finding a basic block is to first find its starting point, and each of these starting points has a name. It's called a leader. It's pretty simple, really. If we can find all the leaders, we can find all the blocks. And lucky for us, there's a really simple 3-step recipe for finding them. Okay, rule 1. The very first instruction of your program, that's always a leader. Easy enough. Rule 2. Any instruction that is the target of a jump, when one line says go to another line, that destination line is a leader. And finally, rule 3, any instruction that comes right after a jump is also a leader. Why? Because it marks the start of a brand new path the code could take. All right, let's actually apply these rules to our example code. So first off, instruction 1 is a leader. Why? Rule 1, it's the start of the program. Done. Now let's scan for any jumps. And yep, there's a go-to that targets instruction 5. So based on rule 2, instruction 5 is a leader. And what about rule 3? The instruction right after a jump is a leader. The jump is on line 4, so the instruction right after it, instruction 6, is our third leader. And that's it. We just used those 3 simple rules and found every single entry point in this code. Okay, now for the final part, and this is the easy bit. A basic block is just a leader and all the instructions that follow it, right up until you hit the next leader. So if we look at our code, our first block starts at leader 1 and runs through instruction 4. The second block, well, it's just that single line at leader 5. And the last block starts at leader 6 and goes all the way to the end. And just like that, we've taken this flat list of instructions and we've uncovered its hidden structure. So we've found our straightaways. These are our basic blocks. What's the next logical step? Well, we need to connect them, right? It's time to actually draw the full map. And in the world of compilers, this is called a flow graph. And again, the idea here is really direct. Each basic block that we just found, that becomes a node, or, a destination on our map. Then we just draw an edge, a line, a road, from one block to another if the program can flow from one to the next. So, to build this thing, the very first step is to take each of those boxes of code that we drew
And we just turn each one into a single node.
Then, it's just a matter of connecting the dots. If a block ends with a jump instruction, we draw an arrow to the block it's jumping to. And if a block doesn't end in a jump, well, the program just falls through to the next block in line, so we draw an arrow there instead. And that's it. Our map is complete.
And this comparison here, it really says it all, doesn't it? On the right, that's a flow graph from our source material, and you can immediately see that loop, right, where block B2 points back to itself. Now, that structure is so obvious in the graph, but try finding it in that flat list of instructions on the left. It's much harder. See, the graph doesn't just show you the code, it reveals the logic. It shows you the loops, the choices, the flow, in a way that plain text just can't.
So, what now? What can a compiler actually do with this powerful new way of seeing things? Now that it has the map, what's the point? Well, by analyzing all the possible paths in this graph, a compiler can find all sorts of amazing opportunities to optimize. It can see, for instance, if you're calculating the exact same thing on two different paths and just get rid of the redundant work. It can spot what's called dead code, blocks that are impossible to reach, and just delete them. It can even shuffle instructions around inside a block to make better use of the processor. And it does all of this without ever changing what your program actually does. But here's where it gets really, really powerful. Think about program testing. Testing only checks the paths that your specific test data happens to run through. But this kind of analysis on the flow graph, it can check every single possible path. All of them. And that lets it find bugs and potential errors that normal testing could miss for years. So when you think about it, what we've really done here is learn to see our code in a completely new dimension. We've kind of peeled back a layer and uncovered this hidden world that lives just beneath the surface of the text. So here's a simple little takeaway for you. The next time you write an if statement, just for a second, picture that fork in the road it creates. Or when you write a while loop, picture that little circle in the graph. You don't have to draw it out or anything, but just holding that mental image can give you a much deeper feel for what you're really building. And that kind of leaves us with one final thought. We just found this simple, really elegant graph hidden inside a list of instructions. It really makes you wonder, doesn't it? What other beautiful, simple structures are hiding in plain sight in all the complex things we build every day, just waiting for us to find the right way to look?